Welcome back. So the last time we looked at the problem of global maxima and minima, and we saw that another such optimization problem played an important role, that is the notion of a constrained optimization problem. That is, you want to optimize f subject to lying on the set G equals 0, right. We saw that to do it directly is almost impossible. So we stated this theorem of Lagrange's multipliers, and then we were in the process of proving it. Again, what's the statement of Lagrange's multipliers? Suppose f and g are two C1 functions defined on some open set, and you consider the set where g is 0, right. So that's a constraint, g being 0. And suppose there is a point A lying on the set where g is 0, where f assumes a maximum or a minimum among all the points lying on g equals 0, right. Then the gradient of f at that point is proportional to the gradient of g at that point, provided the gradient of g at that point is non-zero. So this is the statement of Lagrange's multipliers. We were in the process of proving it. Okay, so let's continue with the proof. We saw that locally g equals 0 can be solved to yield xn as a function of the others, assuming without loss of generality that dg dxn at the point A is not 0 by using the implicit function theorem. Then the function s of a fewer number of variables defined by this, where we replace the last one by this function h, assumes a local extremum, unconstrained local extremum at the point a tilde, which is a1 to an minus 1. So as a consequence, dg dx ds dxi at a tilde is 0. Now what is ds dxi at a tilde? By the chain rule, it's df dxi at a tilde plus df dxn times dh dxi at a tilde. Okay, this is 0. Right. Now what else can we say? We can also say that notice that g of x1 xn minus 1 comma h of x1 to xn minus 1 is identically 0. Why? Because if xn is equal to this, then g is identically 0. That's how h is defined, right. So as a consequence, if you differentiate a function that is identically 0, then the derivative will also be 0, and by the chain rule the same principle holds. This is identically 0. In particular, dg dxi, I mean, maybe we'll call it something else. Let's call it g tilde, right. So dg tilde dxi, dg tilde dxi is equal to this. So dg tilde dxi at a tilde is dg dxi at a plus dg dxn dh dxi. Okay. So in other words, at the point A, we have two equations. One, this is also at A, df dxi at A plus df dxn at A times dh dxi at A tilde is 0, and we have this. Okay. Right. So from this, right, the claim is, from this we can conclude that gradient of f is lambda times gradient of g at the point A. Right. Why is that so? Yeah, basically df dxi is proportional to dh dxi. dg dxi is also proportional to the same vector, right? Mind you, this all of these are for I between 1 and n minus 1. Okay. So df dxi, basically what are we saying? df dxi is proportional to this, and so is this, so which means df dxi is minus df dxn at the point A times this quantity, which is minus dg dxi at the point A divided by dg dxn at the point A. So the minuses cancel themselves out. So when I is between 1 and n minus 1, df dxi is proportional to dg dxi, the proportionality factor being this. And when I equals n, obviously df dxn is equal to a proportionality factor times dg dxn, where this is precisely that proportionality factor, right. So in other words, at the point A, gradient of f equals lambda times gradient of g. Okay. So this is the proof of the method of Lagrange's multipliers. It's not too difficult if you assume the implicit function theorem. That's what's doing all the hard work behind the scenes. And of course the chain rule. Yeah. So how does one use the method of Lagrange's multipliers? Let us go back to the previous example of xy equals xy on the set x square plus y square equals 1, right. So how do you solve this? Optimize, that is, find the global maxima and global minima of this. So this can be written as g equals x square plus y square minus 1 is 0, right. Now f and g are defined on all of Rn to R, right, and they are all smooth on all of Rn to R. What we want to do is to optimize this, right. This is a compact set. So there exists a global maximum of f on this set and a minimum on this set. So suppose A is a point of extremum. A, so in this case it's R2, right. So A in R2 is a point of extremum of f subject to g equals 0. Okay. So in particular A lies on this. What's the gradient of g? The gradient of g, what's the gradient of this? It's dg dx, which is 2x, right, dg dy, which is 2y. This is not 0 if A is not 0, right. Now A equals 0 is certainly not a point of extremum. Note that A equals 0 is not a point of extremum. Why is it not a point of extremum? That requires justification. By the way, it's not obvious, but it's not too difficult. Because if A equals 0 is a point of extremum, what does that mean? It's either a local maximum or a local minimum. So that means near the point A equals 0, either f is larger than or equal to the value. So what is f of 0? This is 0, right. So near 0 comma 0, either f is larger than or equal to 0 for all x and y near 0 comma 0, or it's less than or equal to 0 for all x, y near 0, 0. But that's not possible, because if x and y have the same sign, then f is positive regardless of how small x and y are. But if they have opposite sign, then f is negative regardless of how small x and y are. So A equals, and x square plus y square can be equal to 1, right. I mean so that's the other problem. So it's not a point of extremum for two reasons. One is, even if the constraint was not available, 0 comma 0 is certainly not a point of extremum. The other point is, A equals 0 does not lie on this constraint. G of A is not 0. A is a point of extremum subject to the constraint. So, in particular G of A must be 0, but G of A is non-zero. Okay, so for two reasons. We don't even need the first reason actually. This is good enough to say that A equals 0 is not a point of interest simply because G of A is non-zero there. Okay. So, gradient of A, G of A is non-zero, which means by the method of Lagrange's multipliers, gradient of f of A is lambda gradient of G of A, which means what's the gradient of f? The derivative with respect to x is y, the derivative of y with respect to y is x. 2a1 comma 2a2, right. So we have two equations here. A2 comma a1 is lambda times 2a1 comma 2a2, and a1 square plus a2 square equals 1. Okay. This is 2 lambda times a1 comma a2. We can call this as lambda tilde if you want. So, a2 equals lambda tilde a1, a1 is lambda tilde a2, and a1 square plus a2 square equals 1. You can solve these equations very easily. So, for example, if lambda tilde, so lambda tilde is of course not 0. Why? Because if lambda tilde is 0, then a2 comma a1 is 0 comma 0, which cannot satisfy this, right. So, which means you can simply divide, you can say that a1 is a2 by lambda tilde, but a1 is also lambda tilde a2, right. So, which means lambda tilde square equals 1 or a2 equals 0, right. If a2 is 0, then a1 is plus minus 1, right. Or if lambda tilde square is 1, then you can substitute that here and so on and so forth, right. So, you can you can find out, so what yeah, so you can find out what these things and figure out what the extrema are, and you can easily check that you will attain the maximum value of f will be half and the minimum value will be minus half. Okay. I mean, when lambda tilde square is 1, so that means lambda tilde is plus minus 1, right. So, which means that this is plus minus a2. So, since a1 square plus a2 square equals 1, then a1 and a2 are plus minus 1 by root 2, okay, which is what we want, which is what we obtained in the previous calculation. Okay. So, this is one example. Here is a much nicer example. This is the famous arithmetic mean, geometric mean inequality. So, the example is this: prove that for x1 to xn, all of them non-negative, the arithmetic mean, which is this, is greater than or equal to the geometric mean, which is this, with equality if and only if these x's are equal to each other. This is the famous A.M G.M inequality, and like all good inequalities, it admits many proofs. This is my favorite because it gives you a general way of proving such inequalities, this method of Lagrange's multipliers. So, the proof is as follows. Okay. So, consider, what do we want to do? Basically, what's the idea here? We want to maximize this subject to this as well as this being fixed. So, suppose you take x1 to xn, you sum them up, you take x1 plus x2 plus so on until xn, right. We want to prove that sum is divided by n is larger than this, right. So, among all the x1 to xn such that the sum equals some fixed constant, among all of them, if we maximize this quantity, right, then we will have we will be in a good shape to prove this. So the aim is to maximize. So given x1 naught, x2 naught, so on until xn naught all greater than or equal to 0, right, let C be equal to x1 naught plus x2 naught plus so on until xn naught. We want to prove that x1 naught, x2 naught, xn naught, the nth root, is less than C by n. Okay, this is what we want to do. Right. So actually we shall end up proving that the nth root of x1, x2, so on until xn is less than or equal to C by n for all x1 greater than 0, x2 greater than 0, xn greater than 0, such that x1 plus x2 plus so on until xn equals C. So we will prove something more general than this, that not just these, but if you take any collection of x1 to xn which are positive and whose sum equals this particular value, right, for all of them this is true. Okay. So we will maximize this subject to this constraint. Okay. So consider f of x1 to xn as this, and g of x1 to xn as this function, right. And these are smooth functions, of course, on all of Rn. We want to find the max of f on the set G equals 0, if it exists, okay, and x1 0, x greater than 0, and so on. So we are looking at this set and we want to find the maximum possible value of f if it exists. So first of all, is this set a compact set? Is this compact? Otherwise the maximum need not even exist, right? It may exist, it may not exist. So is this compact? That's the first question. So what is this set again? x1 plus x2 plus so on until xn equals C, where C is of course greater than or equal to 0. Why is C greater than or equal to 0? Because it's the sum of x1 naught so on until xn naught, right, and x1 is greater than 0, x2 is greater than 0, so until xn is greater than 0. This means that this is larger than x1, for instance, so which means x1 is between 0 and C. Likewise, x2 is also between 0 and C, x3 is between 0 and C, and so on. So which means this set here is certainly bounded. It is also closed. Why is it closed? I'll leave this to you as an exercise. Please do this exercise. That will make these concepts of topology a bit clearer. Okay, why is it closed? Okay, so it's a compact set, which means f does assume a max. In fact, this compact set is contained within this rectangle 0 comma C cross 0 comma C and so on. Okay, so we don't need to look at the maximum of f over all x and Rn satisfying this. We just need to look at the maximum of f on this set where such that G is 0. Okay, right, on Q subject to G equals 0. So there are two possibilities. Either this max occurs on the boundary of Q, or this max occurs on the interior of Q. Okay. If it does occur on the interior of Q, then the method of Lagrange's multipliers will be applicable. Method is applicable in this situation. In this situation, it's not applicable, but what is the boundary of Q, right? What is the boundary of Q? It's a place where at least one of the coordinates is either 0 or C. Here, some xi is either 0 or it is C. But if that is the case, since the constraint is g equals 0, which is x1 plus x2 plus so on until xn equals C, right? If some xi is 0, well so if let's say some xi is C, right? If some xi is C, all the others will have to be 0 because they are all greater than or equal to 0 and their sum adds up to C. So if one of them is C, all the others have to be 0. So in other words, we can get rid of this possibility. One of these must be 0. But if one of these is 0, f is 0. Yeah? So, and obviously 0 is certainly not the maximum of f, right? Certainly if you choose some non-zero values of x1 to xn so that their sum is C, then f will be positive, right? So 0 is certainly not the maximum value of f, so this doesn't even apply. So we can happily use the method of Lagrange's multipliers. That is the point. So what is gradient of g here? The gradient of g is dg dx1, etc. This is 1, 1, 1, so on, which is never 0. So which means we can try to use the method of Lagrange's multipliers. Lagrange's multipliers would say that gradient of g of a times lambda is gradient of f of a. Right. What is gradient of f again? It's df dx1, df dx2, and so on. df dxn, right? So what is df dx1? It is x2 until xn. What's df dx2? It's x1, x3, so on until xn. df dx3 is x1, x2, x4 till xn, and so on, right? So what this says is a2 so on until an is lambda times 1. a1, a3 so on until an is lambda times 1, and so on. Okay, a1, a2 so on until an minus 1 is lambda times 1. Yeah. So the easiest way to solve this is you multiply this by a1, you multiply this by a2, and so on, you multiply this by an. So all of these are equal to each other, which means lambda a1 is equal to lambda a2 equals so on until lambda an. So either lambda is 0 or a1 equals a2 equals so on until an. If lambda is 0, that means a2 times so on until an is 0, right? And a1 times so on until an is 0, and so on, right? So if a2 times so on until an is 0, right? So what does that mean? If this is, so if this is 0, one of these must be 0, right? Now if one of these is 0, right, let's say one of these is actually non-zero. Okay, if something is non-zero, right, suppose a few of them are non-zero, right, then there is a, I mean if any of them is 0 rather, so if this is the case, at least one of the ai are 0. But if even one of them is 0, what is the value of f? What is f again? F is the product of all of them, so it is 0, which is certainly not the maximum. So this is irrelevant for us. It's possible, but it's irrelevant. So the maximum is attained when all of them are equal to each other, and when all of them are equal to each other, each of them equals c divided by n, and therefore the maximum, so the maximum of this, so this is less than the nth root of c divided by n raised to n, which is c divided by n. In other words, the maximum of this is indeed c divided by n, which is what we hoped for. Okay, so this is a proof of the A.M G.M inequality using the method of Lagrange's multipliers. It might seem like it's a lot of work, and you may have seen simpler proofs of this inequality, but the point is Lagrange's multipliers gives you a systematic way of proving many such inequalities, right? You fix the right hand side to be something and try to maximize the left hand side, and hope that you actually do have a maximum, that you are on a compact set, then hope that the maximum is not attained on a boundary of something, and if it is attained in the interior, then you hope that the gradient of the constraint is non-zero at that point, and then you solve gradient of f equals lambda times gradient of g. So it's a general sort of a method to prove such inequalities, right? So that's why I like it. Okay. Now the point is, if we examine the proof of this Lagrange's multipliers method, actually examining the proof of the Lagrange multipliers method, we see that we actually need to be able to convert the constraint problem into an unconstrained one of fewer variables. This is exactly what we did. Using the implicit function theorem, we simply solved the constraint by finding one of the coordinates in terms of the others, but it's not necessary to find one coordinate as a function of the others. It's simply enough to convert this problem into an unconstrained one, right? So this motivates the following generalization of the method. Okay, in some sense, a generalization. If you assume the implicit function theorem, then it's a genuine generalization. B, C1 functions, and this is an open set as before. Let A alpha to U be a one-to-one C1 function such that g of y equals 0 and y is in U if and only if y equals alpha of x. That is, you are solving this constraint, except instead of the Lagrange's multipliers method of solving for one variable in terms of the others, we are assuming that all the variables can be solved for in terms of n minus 1 new variables. Okay? So suppose y is alpha of x is the solution of the constraint. Suppose A is a point of extremum of f subject to g equals 0. Assume that the derivative of this function alpha is from Rn minus 1 to Rn at the point alpha inverse of A is an injective linear map. Then gradient of f and gradient of g at this point are parallel. Okay. So this is a generalization of the method of Lagrange's multipliers. In the method of Lagrange's multipliers, we say that if we can solve if the gradient of g is not 0 at that point, so at least dg by dxi is not 0 for some I, then by the implicit function theorem you can solve for that coordinate in terms of the other n-1 coordinates, right. This is somewhat of a generalization in that suppose you can solve for all the coordinates in terms of new variables, new n-1 variables. Okay, you can solve the constraint just like in the method of Lagrange's multipliers, but in a different way. Then assuming that this solution for the old coordinates in terms of the new variables satisfies some property, that is the derivative of this function, this matrix defines an injective linear map. This is equivalent, as we shall see, to the matrix having rank n-1. In that case, the gradient of f and gradient of g are parallel to each other, just like in the method of Lagrange's multipliers. Okay. So this is sort of a generalization of that. Okay. So we will prove this result the next time, and we will use this result as motivation for defining these things called manifolds. Now manifolds are not the main point of this set of lectures, but nonetheless it's useful to know a definition of them, even if you are interested in artificial intelligence and machine learning for that matter. Okay. All right, so we'll stop here. Thank you for joining.